Hello everyone. In this lecture, we'll be studying the altitude hold autopilot system for an aircraft. So here ZB, XB, the body fixed frame, del alpha basically change in angle of attack, V is the total velocity of the aircraft, del theta changing pitch angle, and del gamma change in flight path angle. We can write from figure. We can write del theta equal to del alpha plus del gamma, or del gamma equal to, we can write del theta minus del alpha. So here we can find the vertical height as a function of climb angle. So here the rate of climb or change in vertical height will be written as del H dot equal to V sine del gamma. So del A is basically change in vertical height of the aircraft, and we can also write this expression V sine, in place of delta gamma we can write del theta minus del alpha. And also let's have an assumption for small angle approximation. For small angle we can write sine theta is equivalent to theta, that is So in that condition, if you assume this angle is very small, then we can write, let us define this equation number 1 for small angle equation 1 yields, we can write del H dot equal to V into del theta minus del alpha. Also we know that del Q equal to del theta dot, right? So these are the things already you have discussed in the first course, so I'm not going to detail about it. So here we can add this equation, this equation and this equation. So let us define, this is equation number 2, this is equation number 3. If we add these two equations to the original short period dynamics of the aircraft, so already we had the short period dynamics we have derived in our first course, so I'm not going to repeat it again. So del alpha dot del Q dot equal to, we can write the moment derivatives in the system matrix, Z alpha U naught, moment and force derivative 1 m alpha plus m alpha dot Z alpha divided by U naught mq plus m alpha dot, and the state variable del alpha del Q plus the control matrix Z delta E U naught m del E plus m alpha dot Z del E U naught into del delta E. This is the only control parameter acting elevator. So in this equation, if you add del theta dot and del h dot, so if you add these two terms, this equation and this equation to this equation 3, let us define this equation 3, sorry, 4. We are not going to explain these individual terms inside A matrix and B matrix. So this thing already we have discussed in the first course. So now if we add this equation 2 and 3 to equation 4, we have the state space model. Okay, adding equation 2 and 3 to equation 4, we have the state space model del alpha dot, del q dot, del theta dot, and del h dot equal to the system matrix Z alpha u naught 1 0 0 and m alpha plus m alpha dot Z alpha divided by u naught m cube plus m alpha dot 0 0 0 1 0 0 minus u naught 0 u naught 0. So here, and our state vector del alpha, del q, del theta, del h, and B matrix found to be Z delta E, u naught, m del E plus m alpha dot Z del E divided by u naught and 0 0. And the control input. So here basically let us consider u naught equal to the velocity field, the assumption we are considering. Now we'll be designing autopilot, how we can control this del H over time. This is our how can we maintain the altitude hold of the aircraft. This is very important. The autopilot design. So let us first define the problem. This is basically the natural dynamics. This is basically the natural dynamics of the system. In linear domain, of course, and these are the parameters. We vary to aircraft to aircraft. These are the parameters. So for the particular flight regime, we can get these parameters from the wind tunnel testing. And these are basically stability derivatives, moment and force stability derivatives. So this varies from aircraft to aircraft. Now, example. Use state feedback control to design an altitude hold control system assuming forward speed of the aircraft is held constant by a separate velocity control system. And further neglect the control surface actuator dynamics. Okay. The short period approximation for a particular flight is, this is for a particular flight, the state space model of 10 to be del alpha dot, del q dot, and del theta dot equal to the state space, sorry, the control matrix, no, the system matrix 1.5, 1, 0, minus 4, minus 1, 0, 0, 1, 0, and state vector del alpha, del q, and del theta. This is the state vector, and control vector minus 0.2, minus 8, and 0. So delta. Assume, we are assuming the forward velocity, assume for u naught equal to 61 meter per second. Determine state feedback gain if the closed loop system eigenvalues, closed loop systems eigenvalues are located at, so these are located at, these are desired poles from which we'll find the characteristic equation, and the system should follow that characteristic equation, right? S12 equal to minus 1.5 plus minus 2.5 I, and S34 minus 0.75 plus minus 1 I. So if you notice here carefully, the order of the system matrix is 3 cross 3, but we are having the desired poles, 4 desired poles are given. So we have to come up the system into 4-dimensional space. So let's start the problem solution. Let's first write the state space form, including the altitude dynamics. So here, if you notice here, in this equation, we don't have altitude parameter in this model. So if you include altitude dynamics, including altitude dynamics, we have the state space model del alpha dot, del q dot, del theta dot, and del h dot, and the system matrix yields to be minus 1.5, 1, 0, and 0, minus 4, minus 1, 0, 0, 0, 1, 0, 0, minus 61. This is the, we are adding this row actually, minus 61, 0, 0, 61, 0, and we have the state vector del alpha, del q, del theta, and del h, and we have the control matrix minus 0.2, minus 8, 0, 0, and we have the elevator deflection on the input. Now to here we're gonna use the Bhaskara method to find the control gain parameters. Basically the system complexity is system is complex. There are multiple variables to be controlled. So we can use the numerical method, which is basically Bhaskara method, what you have explained before. So the Bhaskara method, let us use Bhaskara method to find the control parameters or the gain parameters, which is nothing but K equal to P W transpose inverse alpha minus A. So now I think you can design the control, the same step what you have followed before. So first we have to check the system is controllable or not. This is the first criteria to design the controller. So first we can find the P matrix equal to CTRB and A comma B. Okay, here one more thing, we are assuming all states are available for feedback. So states are measurable. Okay. Then only you can design the state, all state feedback based control. So P equal to this and R equal to rank of P. So if you enter, we have R equal to 4. This is the, so it means system is fully controllable. System is controllable. And if you remove this semicolon, we can find also P matrix. Because P matrix is required. In the Bhaskara method, we need to have P matrix also, right? So let's have the P matrix, controllable matrix. So P matrix is found to be minus 0.2, minus 7.7, 20.3, minus 8.5, minus 8, 8.8, 22, 103, 0, minus 8, 8.8, 22, 0, 12.2, minus 18.3, minus 704. This is P matrix. And we can also check whether the system is stable or not. So for that, we need to use system stability. For that, we can use the line omega n, zeta, and poles, and we can use the damp function. And if we enter, we have omega n to be 0, 0, 2.34, and 2.34. And zeta found to be minus 1, 0.5, 0.5, and poles found to be 0, 0, minus 1.25 plus 1.998 I minus 1.25 minus 1.98 I. So if you notice carefully, there are two poles. There are two poles at origin. So if the system has two poles at origin, we can say the system is marginally stable. So in that case, we need to consider, we need to design the control. So first, let's find the initial first let's find the open loop system response. How the system is going to behave in open loop if there's no control in the system. So in that case, we have, if you open loop response, I'll come the code after the end of this lecture. But the open loop response is found to be open loop response is found to be this is we are assuming aircraft is this is the altitude and this is the time and this is in meter. So it is actually going like this. Going like this. So it means the altitude from this plot, altitude, we have the code for this, how the response is coming. We'll further during the end of the lecture, I'll show the code, MATLAB code of this figure. So as expected, altitude is continuously decreasing because there is no control. There is no control applied in the system. So automatically it will decrease the altitude over time. Now we'll use the state feedback control based on the given desired poles, the system, the desired poles, and how we can maintain the altitude hold of this particular example. So for that, let us form the closed loop poles, closed loop desired poles. Desired poles, we can define V equal to minus 1.5 plus 2.5 by 1.5 minus 2.5 I minus 0.75 plus 1I minus 0.75 minus. So this is the desired pole locations. So using the place command, we can find the control gains, right? Place if you use, you'll find A, B, and B. And if you enter, K is found to be 0.77 minus 0.26 minus 1.57 and minus 0.01. These are the control gains of the system. So we have the K, we have A, B, and also we can assume some initial condition also because. So we can find the solution. So augmented system matrix will be augmented system matrix. You can find ACL equal to A minus BK. So in the system is basically all the matrices are known. We know A also, B also, K already found here. So now we can write the code for this particular example. So this is the code. This is the code for this example. So if you notice in the first case, without control, the system is continuously, the height is continuously decreasing here, continuously decreasing. But if you use the control system, state feedback control, so it brings the aircraft the particular altitude. So this is how we can, this is actually particular altitude is brings to the aircraft. So it means the autopilot quickly brings the airplane back to the designated altitude using the state feedback control, what you have here. So this is the basically how we can design altitude hold of an aircraft, which is altitude hold autopilot system. And this code you can use in your MATLAB and you can find the response. This is the response for open loop and this is the response for closed loop system. I hope it is useful to design autopilot for your aircraft. So as of now, we have done many stuff, how to design control for unstable system. Based on eigenvalues, you can define the system stability. And if the system is found to be unstable, you can design control. And we come up optimal control, state feedback control, and also how can develop the stability augmentation system for basically state space model systems. So we are almost end of the control synthesis in linear domain, how we can come up the different control concept. So now we are going to start a new topic, how we can design nonlinear controls for the aircraft. So also we'll have a lot of MATLAB code and yeah, a lot of examples. So let's stop it here. We'll continue from next lecture on new topic, how we can design nonlinear controls for an aircraft. Thank you.